All right, good morning, everyone. Today, Earth Science, we're going to look at lesson 3.12. This is in CK12, and this is the Earth's interior. Okay, so it's kind of a general overview. All right, so this is interesting. It says, how deep can we go into the Earth's interior? Not very deep, for that's for sure. It says the deepest a drill hole has gotten was the Kola Super Deep borehole. Okay, I'm just going to highlight that. Okay, the hole got to 40,230 feet. Okay, that's 12.262 miles. Oops. So 12 miles. That's not very deep. It says it's about a third of the way into the crust in that area. Okay, so the crust must be about, I don't know, 36, 37 miles deep. So learning about what's deeper requires less direct methods. So the question should be, well, how do they know what's deeper than that area if you can't drill down there? Okay, so this is what it is. If someone told you to figure out what's inside the Earth, what would you do? How could you figure out what is inside our planet? How do scientists figure this out? Well, one method, and I mentioned this yesterday, is called seismic. Oops. Oh, I didn't want to do that. Let's go back. Okay, get rid of that. Is seismic waves. Okay. Now, if you know anything about seismic waves, they are released when there's an earthquake. So scientists study earthquake waves to see the Earth's interior. All right. The waves of energy that radiate out from the earthquake's focus. So the focus is this: wherever the earthquake occurs, that is called the focus, which is the actual place where the earthquake, where the slippage occurred, if that makes any sense. So all of a sudden there's a shift in the Earth's crust. And then from there, these seismic waves radiate out and away, almost like if you drop a pebble into a pond and you see the waves radiate from that central location. Okay, so these waves that are created during an earthquake are called seismic waves. Okay, and they get a little more specific, and we'll get into that later. Seismic waves, they go different speeds through different materials. So they travel faster through a solid than maybe through a liquid, or the opposite way around. But their rate of speed changes, just like we were talking yesterday, how light, the speed of light, you see are wavelengths, and the speed of light through different mediums, and a medium could be water or it could be air, glass. It changes as it moves through that medium. So it speeds up or it slows down, which then gives you sometimes a distorted image. Okay, so seismic waves go different speeds through different materials. They change the speed. Okay, I'm going to highlight this. I know I'm highlighting a lot. They change the speed when they go from one type of material to another, and this causes them to bend. Okay, so sort of like refract. Sudden seismic waves do not travel through liquids or gases. Oh, there you go. So some waves do not travel. They just stop. Scientists use this information to understand what's inside. So if they know that certain waves don't travel through a liquid or a gas, if all of a sudden it just kind of isn't there, then they know, oh, that portion of the Earth must be liquid. All right. This gets a little bit. We're gonna go into this down the road. Okay. Scientists also study meteorites, and meteorites to learn about the Earth's interior. Meteorites formed in the early solar system. Okay. These objects represent early solar system materials, and there's a meteorite right there. Some meteorites are made of iron and nickel. Iron and nickel are two metals, and they're actually two elements. And they're thought to be very similar to the Earth's core. And right there is an iron meteorite. Density. So the Earth's overall density, and density is how much matters within a certain area, but the Earth's overall density is higher than the density of just rocks. So the core must be made of something more dense, such as a metal. That's how they've come to the conclusion that the inner core is iron and nickel. It's a metal. Also, since the Earth has a magnetic field, there must be metal within the planet. So iron and nickel are both magnetic. That also leads to that conclusion or that theory. Okay, so in summary for this unit, different types of seismic waves, those are the waves released during earthquakes, they behave differently in different materials. Their behavior can tell scientists about the material through which they travel. Earth must contain metal, its density, and the fact that it has a magnetic field require that. So they know that inside the Earth there must be some metal portion of it because the density is more than rock. And we also know about this magnetic field. In order to have a magnetic field, you need to have magnetic metals such as iron and nickel. And since meteorites formed early in the solar system, they indicate something about our Earth's interior. Okay, I'm going to play this little video for you on seismic waves. All right, so sit back and relax.
Earthquakes generate two main types of seismic or shock waves, body wave and surface wave. Body waves travel through the interior of the Earth. The fastest of these are primary or P waves. These compressional waves move faster in dense rock and slower in fluids. Thus, their speed and direction change. Because they are deflected by the Earth's core, P waves are not seen in the so-called shadow zone. The slowest body waves are secondary, or S waves. S waves are elastic shear waves that move material sideways at right angles to their direction of travel. Because secondary waves travel only through solids, they do not penetrate the Earth's outer molten core. For this reason, there is also an S-wave shadow zone. The slower seismic surface waves do not penetrate the Earth's interior, but follow the surface. One type of surface wave, the love wave, travels in a circular motion and causes damage by displacing materials horizontally. Love waves can be very damaging. This cracked pavement and these twisted railroad tracks clearly demonstrate their destructive power. Earthquake damage also results from Rayleigh waves, surface waves which deform materials vertically.
All right, cancel, close this up. All right, that was okay. Not as good as I'd hoped, honestly. But you see the difference, and it's just talking about how they're able to determine what's inside the Earth. Okay, so what I'd like you to do now is I'm going to post this assignment, and I want you to do the practice. Also, do me a favor, make sure you go back through and highlight this the way I've done this. These are kind of the key points. All right, good luck with this, and thank you.